Thanks for the introduction. I'm Mark Lindsay. I'm from the CSIRO and also from DARE, the Minerals Exemplar there. And we're going to explore a few different topics in this presentation. And I will explain what I mean by sustainability, because that's a bit of a buzzword, but also has a number of embedded meanings within that. So first of all, I'd just like to acknowledge the traditional owners of the lands that we're meeting on today, and that's around Australia, and pay respect to their elders past and present. For me, that's the Whadjuk people of the Noongar Nation, and I'm speaking from Walyalup in Fremantle. And also, I'd like to acknowledge a whole lot of people that I've had really interesting and inspiring discussions with, who challenged me on my thinking. Just that list of people there on the left-hand side, as well as various companies that have supplied the data that we're experimenting with in our research efforts. And some of the researchers that are working directly with me and the Minerals 4D initiative, this digitalisation of the mining value chain. You'll see Maria there, of course, and Fabian, both DARE PhD candidates, and a few others that I'm working with through various centres and as PhD programs. So like all good presentations, I'm going to start with food. And this is a loaf of bread, but this loaf of bread in some ways represents an ore deposit. So ore deposits and loaves of breads kind of form the same way in that we add a few ingredients like flour, water, a bit of yeast, some volatiles. We might add some butter or cream depending on your taste, and a bit of salt for flavour. And then we start kneading it, we start deforming it, putting it under pressure, and eventually we'll add some heat to it, put it in the oven or tectonically bury these things, cook them until we form a loaf of bread or our ore deposit. Now, one of the challenges that the mining industry faces is saying, well, actually now we've got our ore deposit, we'd like our salt back, please. The salt here might be something like nickel or copper. These are the kind of grades that you might have of salt in a loaf of bread that you might expect from a mineral deposit. It's quite a hard thing to do to get that salt back out. Now, one of our other challenges, of course, is that there are a number of loaves of breads, and in fact, thousands, if not tens of thousands of loaves of breads that we need to assess the salt content of to see whether or not they're actually economic for salt extraction. And in this bakery here, we have many different types, different shapes, different locations as well. And we need to systematically go through all of these different loaves to find which ones are the ones that are worthwhile extracting minerals from. Now, perhaps that was in the old days that we're able to walk through the bakery and have a look at these things, but now it's more like this, where we might have a window where there's a few loaves of bread that we can assess, can look at, can have easy access to. But in fact, most of them are gone. And in fact, most of the loaves of bread or the ore deposits that we have access to are towards the back of that bakery. And what we might need to do is start using data that tells us about where the location of those loaves of breads are, using either geophysics or drilling or other clever modelling techniques to have a better understanding of what the structure of that bakery is and where we need to look and how much we need to spend to do it. Now, with other economic, environmental, social and governance issues as well, is that our bakery is starting to look like this. And all these things are in place for a very good reason. We need environmental controls. We need to understand the governance of the operation itself and have a good understanding of the social impacts of mining operations in the locations that we decide to build a mine. But this does make the location and decisions around what is actually a sustainable mineral deposit quite an interesting one. So once we actually have the salt from our deposit, and maybe that was done 20 years ago, industry might come back to us and say, you know what, we also need the yeast as well. Can you get that for us too? And this is going back to the sloppy piles of dough that are lying around that have had most of the salt removed, and then going and trying to extract the yeast from that as well. And this is quite relevant for battery minerals at the moment, where we need cobalt, which was originally a deleterious or a waste product, from those nickel deposits as well. So this is quite a complex problem that the minerals industry faces. CSIRO does actually deal with many of these different phases of the mining value chain that you can see here on the right-hand side, from exploration and discovery to characterizing ore deposits once they've been found, to evaluating whether or not they are economic or sustainable for extraction, and then mining, sorting the waste from the ore, and then processing that ore into something that is to a concentrate that can be shipped or refined and then sent to market. What we're dealing with here is that we're essentially looking for deeper discoveries. All the surface discoveries have been made. We need greater metal supply to supply the green transition. So this is things like copper, nickel, cobalt, rare earths, vanadium, titanium. Some of these minerals are quite hard to find, lithium as well. But all at the same time, trying to do this with less water, acid, and energy to, so we're not end up using more energy to supply the great green transition. So our efforts are really in, as early as possible, integrating data that is relevant for not just exploration or characterization or evaluation and planning, but that is relevant for everything along this mining or minerals value chain. At the same time, quantifying uncertainty as we move through the minerals value chain to try and see what the propagating effects of that uncertainty might be on our decisions. And most of this is a multiple scale spatial temporal issue that we have to deal with, because not only are we looking from large scales when we're looking for a valid mining district, we're also looking at different down to small scales in terms of a mine, but we're also looking at different temporal scales where exploration and discovery might take 5 years, but the development of a mine from characterization, planning, and the actual building of the infrastructure might take decades. So we're just trying to link up these different parts of the mining minerals value chain into something where the data can flow through. So it's not just a one-way like the material flow is through a minerals value chain, but that information and knowledge can loop its way through. It can be either fed down or fed back up. So what you learn in mining or processing can be used for exploration and discovery, characterization, and so on. So I'm not going to talk about all of that today, but what I will do is start on talking about a little bit about the uncertainties that we might deal with when we're talking about the minerals value chain. So there is an aleatory uncertainty consideration, which is essentially measurement error. So this is the error that's inherent in the measurement itself, either positional or an engineering error associated with the sensor itself. It's not ever going to be infinitely precise. We're also talking mostly in this presentation about the epistemic uncertainty, and this is where we have incomplete knowledge, and this is where we might need to join the dots through some sort of interpolation or prediction, where we're missing information and we have to build a model. These models naturally are simplifications of reality and rely on interpolation or extrapolation. So we might need to do something like this, which is we've got an obvious geological contact trace, and we've got a number of different options we might choose, and we might want to explore what all the possibilities might be there. Some of the other ones, which are a little more cultural and related to people, are our linguistic uncertainties. So this is where there is vagueness about what our actual aims are within a minerals value chain, or ambiguity in the way that we communicate with each other. So this is particularly apparent when we're talking about different domains or different activities within the minerals value chain. And that could be process engineers talking to mining engineers, or geologists talking to mining engineers, or lawyers talking to accountants, or the CEO talking to the logistics people. So sometimes the issues, things that are really important, are underspecified. And of course, our value uncertainties, where we're constantly trying to balance trade-offs between the social, economic, and environmental constraints that we're working within. And when I'm talking about multi-scale, I'm talking about the fact that as geologists, we rely a lot on on pattern recognition, recognizing certain patterns within different data sets at different scales. So these 4 different images here are of vastly different scales. You can see the scale bars there. We're talking about tens of kilometers in this magnetic image. We've got, if we move down to the bottom left, we're talking about meters. You can see the people there. It's a drone shot. Then we've got the hand sample scale, about centimeters here, and then we're at millimeters. And of course, with some of the more advanced sensing techniques, electron microscopes and so on, we're talking about micro and nanometers. But in these 3 or 4 images, I should say, we do have similar patterns, similar shapes, these sigmoidal shapes, which we might say, oh, do they represent the same thing? And we rely on these to link different scales with each other. So if we see a persistent pattern, some sort of fractal relationship, self-affine or self-similar relationship between these things, we might say, oh, similar processes have affected these rocks. And we might make an interpretation that, say, in this case, might be shearing, where we've had movement top right to the top to the right sense of shear, and use that as some constraint for a model that we're trying to build and understand how the Earth works. So trying to manage this sense of scale across multiple data sets does require a certain amount of integration and knowledge coming from the person who is looking at these different data sets, because a lot of the data sets that we have to use to try and transcend these scales are not similar the whole way through, either in the spatial scale that they occupy, but also the different properties that they represent. As you can see in this image here, their imaging depth. So this is just a representation of a typical set of data that you might use when you're exploring for, say, gold in Western Australia. You might be relying on drilling, for example, which is at the bottom left there. And we've got data resolution is quite small. So we can get very small and precise measurements from those drilling, from diamond drilling. And that means extracting cylinders of core from the ground, and you can perform so many different analyses on these diamond drill cores. You end up with just such a diverse set of information that can generate some really useful knowledge through the entire minerals value chain. One of the drawbacks, of course, is that its imaging depth is quite small. The deeper you go, the far more expensive it is. The analytical techniques can be expensive as well. But for the purposes of this diagram here, it's essentially a 1D line that is sampling a very small part of the Earth, but sampling it very in great detail. As we move to the left, move to the right, we can see our geological map. This has a slightly larger data resolution, maybe slightly, depending on what the kind of geological map is, but it might have a slightly deeper imaging depth. You might have a bedrock interpretation. So this is the rock underneath the sandy cover or vegetation, soil and things like that. And this again has probably a number of different geological properties associated with each of the polygons that represent a different rock unit. It might represent different rock types and mineralogy. It could even be associated with different petrophysical properties such as density, magnetic susceptibility, and conductivity. And the deeper and the larger scale we get, so we're moving to gravity and density, and these would be 2D images of the surface of the Earth. We do get better coverage. We also have greater spatial extent as well, but we tend to move to a more univariate property representation. So in this case, we have a gravity data set that just represents density. These are the data sets I will be focusing on in this presentation. But we have magnetics as well, which represents magnetic properties of the rocks. And as we move even further to the right-hand side, we've got reflection seismic. This is a section view of the Earth, not map view. And this responds to velocity and density. And this is a very useful way of understanding structure. But again, it's basically a 2D plane through the Earth. They're quite expensive to collect. And it does have a good representation of that plane. But then, of course, you need to think about everything else that's between your seismic sections. And that could be hundreds of kilometers that you need to consider. And then we have our 3D data sets, which are essentially inversion models from the collected data from, say, gravity or magnetics. They have a deeper imaging depth, but then we also have our data resolutions getting bigger and bigger and bigger. So the detail that you can get from these tends to be not as great as what you might have from a geological map or even the 2D interpretations. And finally, in this image, we have MT, which is magnetotellurics. This has a resistivity property associated with it. Very deep sensing and can be quite large in scale. But again, the data resolution of these tends to be even greater as well. So the spatial, the cell sizes are quite large. What we also need to consider when we're moving downscale, so when we're moving downscale into, say, looking at drill holes and things like drill core, or even to ore characterization, is that in this image here, we're starting out at the mega scale. So this is space and airborne analysis. And this is where we might collect our data from, the gravity, magnetic, and in some cases, electromagnetic data. To the macro scale, where we have someone on the ground with an instrument sampling and zapping rocks. We also have our downhole drilling rig here. So this is the macro scale. And then as we get closer and closer to ore, the mining of ore, the sorting of ore, and then the processing of it, it's more and more important that we consider these meso, micro, and nanoscale characteristics, which essentially must come from drilling. And a lot of these characteristics are collected during exploration to try and better understand the deportment of minerals in the rock, but they are almost critical when you're trying to configure a processing plant or a grinding circuit, a comminution process. Understanding the different mineralogy is a key concern when you're investing in essentially what is the biggest investment that you'll have with a mine is the processing plant. So when we, as geologists, work on trying to find a mineral deposit, so this is going back into the exploration phase. This is quite a large view in terms of scale. And we might be talking about kilometers to tens of kilometers here, and deliberately not showing a scale here because it could be continental scale to tens of kilometers. The kinds of images that we look at are ones such as this in the top left-hand side. This is a gravity image. The lighter colors, the whiter colors are what we would assume to be a greater gravity anomaly, so a stronger gravity anomaly, and this is associated with gravitational acceleration, so more gravitational acceleration in these places. And that we assume is related to higher density of rocks that are sitting in that location somewhere, right? Either near the surface or deeper. And we might take a map view here, we might draw a profile across that, and where we see these steeper contours in the profile view, we would assume because there's quite a rapid change from a low density to a high, or a high density, low gravity to a high gravity anomaly, or a high gravity to a low gravity anomaly, it might be associated with some sort of structure or change in rock type. So for example, if we had a look at this one here, we've got these lines which represent faults and so on. The steeper gradients in this profile here are associated with where someone might draw a fault trace, for example. What we often don't do is look at which data are available or are there present to support our interpretations. So if you have a look at this image on the right-hand side, I've plotted all the stations for that gravity image. They're quite well clustered and sparse in locations as well. So while we might be confident saying that this is a steep gradient here, really it's supported by 2 data points. Okay. So if that is an important structure, this one over here, it's supported by 2 data points. We do need to understand the spatial error that is associated with these grids that we use for interpretation, as well as, say, you might be more confident with any interpretation in this part of the profile here because it's got a greater data set density associated with it. So this spatial error, this data density problem is one, or consideration is one that I'll be focusing on in the next few slides. Because we're not just worried about where the position of these different faults are, but if we're looking at different geophysical anomalies, we might want to know what their shape are and how deep in the crust they are. These more dense anomalies is generally associated with the location of mineral deposits, especially the edges of them. So understanding their shape and their depth is a really important consideration if we think that a mineral deposit might be located somewhere. If it's too deep, it's simply not going to be a viable target. So in this example here, we've got, this is just to show the ambiguity of geophysics, which the geophysicists or physicists will be very familiar with. But we have a modeled body C at a particular density here, which recreates this curve there. And that curve is just a synthetic gravity signal that you might measure from a gravity survey. The problem that we face, of course, is that B, which is deeper, slightly more dense, slightly less dense, but also recreates this curve in almost exactly the same way. And then we also have this very dense body here, A, which also recreates the same curve. So we often have to test out different scenarios when we're doing this gravity or geophysical modeling to try and reconcile which of these is the most plausible. So this is just an example how people might do that. And this is just a forward model that I made from a study in the Capricorn, where we basically digitize a whole series of polygons in a section here. We assign some petrophysical properties, such as density or magnetic susceptibility, and we try and match that to what the measured gravity is. Now, in fact, this isn't the measured gravity or the measured magnetics. These have been sampled from the grid. So this is coming from an interpolated product. I don't actually know where the data points are on this. They are points, but they're grid points. So part of this is I'm quite confident that this is a reasonable geological model. So this is the petrophysical model here. Looking at the different petrophysical distributions, I can then make a geological model here. And this is based on surface. This is constrained by certain surface measurements as well, such as strike and dip, other observations that you might make when you're walking around on the surface of the Earth. But I'm modeling this against the geophysics, which I consider to be the truth. But it's not actually the truth, it's an interpolation, it's an estimation. And some parts of this line might be quite wobbly, depending on what the data density is. But I don't know what it is, because I haven't really shown it there. And when we're talking about multi-scale as well, there are some recent examples of how we might use different data analytic techniques for scaling gridded images. So this could be satellite images, as you can see here. This is an autoencoder example. It's quite a good one, relatively effective when it's using satellite images. This is the publication down on the right, down on the bottom right. I also tried it myself. Not too bad at reconstructing a photo. There's my friend Amro. But when you look at the geophysics on the bottom as well, I don't think it's very good at reconstructing geophysics. So this is reconstructing it from only 25% of the available data. It's probably better at faces because I think we have more faces in our training sets. Don't have a lot of geophysics. So it might work better if we added more geophysics into that. But then again, that's a grid. We don't know where the data points are. There is no spatial error understanding of where that is. So in the application to exploration geophysics, I think tracking uncertainty is very important. So understanding, using it as an accounting, a way of accounting for changes of scales, but also adding in extra data. So if you're going to add in or spend money on collecting more data, what's the impact on your geophysical data, geophysical models? And maybe not just infill, but actually replacing the entire data set with something far more dense. This is another example. This is super resolution. So this is using generative adversarial networks. Again, not a bad, quite an impressive result there. Talking about the super resolution. So coming from low resolution magnetics to high resolution magnetics. But again, one of the things that we find really important is tracking that uncertainty. So just to walk you through a scenario where this might be really, where an exploration company might find themselves, they might be looking at the entirety of Australia, trying to find where a prospective terrain might be for some critical metals. And in this example here, we can look at the Kimberley region up here in the north of Western Australia here. And again, we're looking at the gravity model of Australia. where high values, the lighter areas where the gravitational acceleration or the gravity anomalies are stronger, and then the darker ones are where they're negative. Now, of course, looking at this image over here on the left, you don't actually understand. You've got no idea what the data density is, and how rubbery any of those interpolations, any of those predictions between data points are. So this is the data density here on the right, obviously, where the deeper purple colors are where there's greater density of data. And understanding that hopefully will become apparent. The importance of that will become apparent as I move on. So just as a quick aside, the modeling that I've been using to produce these grids is essentially geostatistical. We're producing a spatial error, and this is using something called INLA, which is an integrated nested approximation, essentially a Bayesian approximation technique. There's the reference there. What I like about it is that it is fast. As you can see from this table here, we've got a number of different methods. We've got fixed rank kriging, INLA, lattice Krig, NGCV. This is a very popular package in R, MRA, and GStat. GStat offers typical ordinary kriging type or indicated kriging variants, much faster than the rest of them by an order of magnitude. But recent release by these guys out of University of Wollongong, so fixed rank kriging version 2 is quick, really easy to use. I recommend having a look at that. We're investigating using this at the same time as INLA for this kind of work. So back to the exploration scenario, we're looking around the Kimberley region here, and looking at where the location of various mineral deposits are and their types. So we've got cobalt, vanadium, nickel, and rare earths. We see that the eastern Kimberley is a lot more prospective. So let's have a look through there. This is a place called the Halls Creek Origin. So we zoom in to this part of the world, and when we take into account the data distributions, so you can see the data distribution here, these purple dots. You can also see the spatial error. So just like with the gravity images, high spatial error is represented by the lighter colors, darker with low spatial error. Basically, you can see the same patterns. Where there is data, there is low spatial error, and where there is where there is no data, there is high spatial errors. And we can also measure that. And I think this is important, is that we can take, say, the mean standard deviation of this particular image and see that it increases quite significantly from the image that we've got, or the model that we have of the Kimberley region itself, because we've got less data to work with. Okay. So some of these locations the estimates might be quite wobbly because we're a long way from data points. As we zoom in again to this particular region through here, which is, let's call it the Savannah region, because there is a nickel mine in there called Savannah, in the central Halls Creek origin, we even jump up quite markedly in our mean standard deviation as well. So we're tracking how much error that we're imparting into our model because we're using less data in our interpolation. Okay. Now, then it's just showing how there's some of the structures that you might interpret from these images. As an exploration manager, you might be quite uncomfortable with the fact that knowing that and actually seeing that some of those images are quite fuzzy, you might invest in some gravity surveys. Looking around, you see an airborne survey has been conducted and released by the Western Australian government. So this is that one here. And you can see that this one is far, far, far more densely populated than the regional survey here. It's flown in lines, there's tie lines and everything else. And we end up with, because it's a much more dense survey, we end up with a much lower standard deviation or average standard deviation across that exploration area. And in fact, I'll do a comparison in a minute that shows, in fact, you do start to see a lot more geologic structure in that model. And then if you want to get down to, say, a camp scale, or where you're actually trying to target particular deposits, you might invest in an airborne gravity gradiometry survey. Yes, they're expensive, But as you can see here, the image that you get back is quite spectacular in the types of geology that you might be able to detect or to interpret, such as this intrusion here, faults and shears through here, pull apart structures and so on, folding, shearing, all of that's great stuff. But more importantly, you can track the fact that, yes, you are reducing the error or the potential error in your model by investing in a denser gravity survey. And this is just a comparison of the airborne survey, airborne gravity survey here with the regional. You can start to see a lot more structure in these. And the regional survey with the airborne gradiometry survey, not only is the error going down, but you also start to see a lot more structure because you've got tighter or much shorter distance between data points. So these are the kinds of things that we're talking about. Now, this is not a new problem, of course, and this is what would be called a change of support problem that needs to be addressed. And there are frameworks for that, which we're investigating for this particular application. So why, again, just addressing why the spatial, or at least acknowledging spatial error is important. It's because when we're saying using things like geophysical inversion, where we're trying to build a 3D petrophysical distribution of the Earth to try and understand what the structure might be, is that we often use the objective function of that inversion. So what the model is being measured against is gridded data. Unless you supply that spatial error, it doesn't know where the data points are, and in fact, it doesn't know where the wobbly predictions are as well. So this is something that we're thinking about. It's like, okay, what can we do with this spatial error estimate, aside from just tracking the increase or decrease in spatial error as you zoom in or zoom out or add in other data sets. Same thing can be said for data fusion when we're using machine learning or AI. If we're trying to merge these data sets together, such as lithology or whether presence or absence of faults, so that if we're using grids, and this doesn't just count for geophysics, but anything that is interpolated, if we don't account for that spatial error, it just assumes all values in those grids are true, okay? And there's no error, there's nothing so there's no constraint. And this could be used as some sort of, the spatial error might be used as some sort of a weighting matrix for making predictions about the presence or absence of particular geological objects that are important for mineralisation or for resource management or whatever. So some of the work that we're looking at the moment is, this is by Moser Kademi, UniSA. He's looking at the sensitivity of our inversion results to inversions themselves. So we've taken, this is a location in the Eastern Ilgan, gold prospective location. We've taken a gravity survey of almost 4,000 points and randomly sampling a set of points from that survey, 300, 600, 1,000 and 1,500, running all of those different randomly sampled data sets through inversion to see what the differences might be. And these are just preliminary results here, but it's quite interesting in seeing the difference between, say, a data set, or the 50 models that have been randomly sampled, or sorry, 50 data sets that have been randomly sampled from that data set, and then compared against each other. So we have a mean density across in this area. So that's the result from the inversion. This section is taken through the gold prospective location, and we can also see what the variation between those 50 models might be. And you can see the variation is in the areas that are probably the most interesting in terms of structure and trying to locate gold mineralization. So in some ways, it's actually a good thing to know that this is how wobbly our inversion might be. Same thing with 600 stations, but in fact, what you start to see is different structures appearing in these, or different anomalies appearing in these inversions, which you need to take into consideration that if you've only got 300, 600, or 1,000 points, how dependent it is on that actual, the density of data that you put into the inversion itself. And of course, we're also considering these modeling constraints. So acknowledging that there is sparse data, that we might be also using the spatial error as a constraint against overfitting in inversion. But also that the imaging depth is related to our station spacing. So the further away that our stations are, the deeper the image, the deeper the minimum image depth might be. So the closer they are, we might see into the very near surface. If they're quite a long way apart, we might be only looking at to the first. We might only be seeing from the first kilometre onwards, so and deeper. And you can see from this left-hand side here where we've got 25-meter station spacing that these longer wavelength signals that you see here is essentially not well. You get a higher frequency with a much shorter station spacing. These would be probably reflecting the near surface signal, the near surface geology. This would be more than likely looking at the deeper geology. And something that we don't do very well is considering this station spacing and when we're merging different data sets together, either as joint inversion or in data fusion, is that say if we have an airborne survey such as EM that might be looking at the top 400 meters of the crust, and then we just chuck it in with a model with gravity, for example, that is looking at say 500 meters down. And 500, and they're not actually imaging the same thing, but we assume that they are. So this is something that we at least can, when we're looking at station spacing in spatial error, use as a constraint to make sure that we're actually imaging the same part of the crust at the same time. We're not just trying to say, oh, the gravity looks at the near surface and so does the EM when it actually doesn't. I think I'll probably finish on this last bit here, but the biggest problem that we face, and I don't actually have a solution for this, but it's this scale from the camp, which is 100, say, kilometers, down to the mine scale. And some of the density estimation techniques or geophysical techniques that we can use to estimate density, there's a bit of a gap in what we can actually reliably employ to understand the Earth. So what we would like is a density model of, say, a mine, because this helps us with ore targeting, and could also help us with our tonnage estimation. If we had a full density realization of a mine, it might give us better tonnage estimates, because often they're not constrained by a lot of data. And in some ways, the tonnage estimates are assuming that all the geological units within the mine that are being mined are homogeneous in their density structure, which we know aren't. And in fact, it's probably the opposite. They're more than likely to be a lot more complex. So if we had a 3D density model of the mines, it would be a really useful thing to get a better and more sustainable estimate of what the metal contained within a mine might be. But just as a quick demonstration of the difficulty in this is the airborne gradiometry data. You can see the data points there. You can see the tie lines as well. But because this is a moving platform problem, the best resolution we can expect from these kinds of surveys is about 150 meters. So that's the Savannah pit there. That's 150 meters square there. So we have an estimate of that particular mine of 9 spots, 9 samples. And we're sort of back to where we started from, is that we still don't have a great density estimation of the mine at that resolution. And that's the gravity image that you get from there. So it's not probably all that useful for mine scale modeling. So what can we do? Well, we can look at drill core for prediction, inference, and imputation. Fabian Leal, part of his PhD project, is trying to use this mine scale data, and looking at something called deep rigging, which is deep learning and rigging combined. At the moment, he's producing some models looking at pyrite, pyrrhotite, chalcopyrite, and chromium RQD, and the coordinates of the samples themselves to predict density in a mine. More importantly, it's uncertainty aware, so it'll give you an uncertainty on the estimation because it's kriging, but also being a deep learning technique tends to not have explainability, but Fabian does, and he's working on how that can be achieved. And I won't steal his thunder. I'm sure he'll have an opportunity to present this in the near future. It's very cool. We also have smaller scale surveys such as ground gravity, which might be an option, except getting access to the ground now because of social and governance issues around ground access to exploration locations is tricky. There's also muon tomography and passive seismic, which density will respond to density changes in the Earth as well. But each of these have their own trade-offs too. And of course, as we move further down the scales, we have our core here. We can use things like CT, computed tomography, and micro CT, say of BIF or of any type of core. And we can see the density distribution at very, very high resolution here. This is low resolution CT, but in terms of what we need to know about the density distribution in these drill cores, it's quite high and it's very useful. And that what we can do is say take a micro CT image of core here from from a nickel mine and see the deportment of the high density materials, which are really important for things to understand how they might respond to flotation, to separate minerals, the dense minerals from the less dense minerals, or how they might respond to comminution, grinding, and processing of the ores themselves. So I've taken you on a bit of a whirlwind tour of what we're trying to do. So trying to achieve a look at deeper discoveries for greater metal supply, less water, acid, and energy. But data integration is the key thing here. And bringing this in as early as possible to better understand, say, for example, what the density distributions might be at over multiple scales, understanding density distribution through a potential mine as early as possible would enable us to achieve a more sustainable mining industry. So rather than us getting everything moving, investing in something that may or may not actually be easily exploited because of a number of different processing, geotechnical, or mining issues, the sooner we can get this information, the better. But there are some challenges there, as in that camp to mine scale jump that we have to fill, and also acknowledging that uncertainty is present at each step of the way, and then of course working across those multiple temporal scales. So I will leave it there, and thanks for your attention.